Hey guys, welcome to the next video on Diels Alder. So in the previous videos, we covered how stereochemistry works when we have a substituent on the diene and when we have a substituent on the dienophyte, but not a situation where we can have a substituent on both the diene and dienophyte. So now we're going to cover that sort of situation. All right. And so I gave this little schematic to you guys in the first, one of the previous videos. Right. Here's our diene. And here's our dienophyte. We have a trans group, the cis groups, and we have these non-chiral groups, no stereochem, so I'll just put an M. Alright, when talking about the dienophyte, I'm going to just draw the group, this Y substituent, again, doesn't really matter what it is, Z, and I'm going to put here an electron withdrawing group. Okay, so let's shift this over. So when we have substituents on the diene and on the dienophyte, right, and we do a Diels Alder, we're going to get two products. These are going to be called the endo and then the exo product. All right, so what does this mean? So when we do the Diels Alder, here's our 6-member ring that we're getting. And let's number here just to keep it consistent. 1, 2, 3, 4, 5, 6. All right. 1, 2, 3, 4, 5, 6. We know the double bond is going to be formed at carbon 2 and 3. Put that there. Now, the substituent with M, right, coming off of carbons 2 and 3, they're not going to have any stereochem because they're coming off of carbons with double bonds, so we just draw a solid line. All right. And we have off carbon 1 a trans group labeled as T and a cis group labeled as C. Right? And same thing for 4. So what I'm going to do is I'm going to just draw them planar for now. All right. No stereochem. Of carbon 6, we have a Y group and our electron withdrawing group. So let's draw those also. Y, EWG. And off carbon 5, we had Z and Y. So let's put that also. Okay. And so this is everything planar. Now, in the Diels Alder, like I said, when we have these two, when we have substituents on both the diene and the dienophyte, we can get two products called the endo and then the exo product. This refers to the stereochemistry revolving around this trans group and the electron withdrawing group, and then same thing for this trans group. In the endo product, the trans group, right, whatever group was on that trans position, must have the same stereochemistry as the electron withdrawing group. All right, and same for both of these trans groups, they both have to have the same stereochemistry of the electron withdrawing group. Then that means that the cis group would have opposite stereochem. The exo is the opposite. This will have the same stereochemistry as the electron withdrawing group. Okay, so let's show you guys. Well, I'm going to show you guys what I mean by that. So I'm going to erase everything here. So I'm going to arbitrarily pick to make the trans group right here. It's going to be dashed. All right. It could have just as easily been wedged. You have it dashed, right? And remember, we still have to keep our stereochemistry rules of how the diene and dienophyte work. These trans groups are the same side relative to each other, right? When we say they're trans, we mean if you compare this trans group compared to this double bond, yes, it's trans to the rest of the diene, but it is still on the same side as the other trans group, so they must have the same stereochemistry. So if I make this guy dashed, the trans group on carbon 4 must also be dashed. Now let's look at the cis groups. Remember that the trans and the cis are not on the same side, so if one is wedged, the other is dashed. And the relationship still holds that these two cis groups are on the same side as each other. So if I make this cis wedged, this one also has to be wedged. All right, so let's draw a wedge. All right. Now we just have to worry about our diene file over here. Right? What happens to this guy? We said that the endo product, that the electron withdrawing group on the diene file must have the same stereochemistry as the trans groups. These four, right? So if we made the trans group dashed, then the electron withdrawing group is now dashed. All right, and remember, to keep our rules of how stereochemistry works on the diene file, the electron withdrawing group is on the same side of the double bond as this Z group. So we put the Z group also dashed. These Y groups are on opposite sides of the double bond from the electron withdrawing group and our Z group. So if our electron withdrawing group is dashed, we make that Y group wedged. And we'll do some practice problems because I know that with these M, T's, C's, Y, and Z's, it's a little bit hard to see. And so that's the endo product. The exo product, which is the minor product, and remember, no stereochemistry on these on the substituents on that new double bond. The exo product, right, is just going to be where the cis groups have the same stereochemistry as the electron withdrawing group. So let's do this. Let's stick with keeping the trans group dashed, and this is wedged. But now what's going to happen is I'm going to make the electron withdrawing group wedged. All right, so the way we talk about the relationship between the electron withdrawing group and the trans substituents in the endo product is they are cis to each other, same side, right? Dashed, dashed. These cis groups right here, compared to the EWG, are trans, opposite stereochem. Okay? And remember, if we make the electron withdrawing group wedged, because that substituent is on the same side, it must also be wedged. And then the Z groups will have the Y groups will have opposite stereochemistry. All right? And that is going to be the exo product. It's the minor product. Now, what's the relationship between endo and exo groups? All right? So when talking about endo and exo, if you look, we don't need to talk about the carbons with the M groups, right? There's no chirality there, right? Oh, and when I mean relationship, I mean like the stereoisomer stereoisomerism relationship. So if you look, the only difference between the endo and exo is that the stereochemistry of the electron withdrawing group has changed, right? Here it's dashed, and then so is the Z. Here it's wedged, so is Z. How many chiral centers do we have? 1, 2, 3, 4. All right, and we have 4 chiral centers. These two did not change, but these two did. So when we have a compound with more than one chiral center, and at least one of them stayed the same, we call these diastereomers. Right? Flashbacks to Orgo 1. You should know that these are diastereomers to each other. You should also know that these also create enantiomers, so you're going to get the endo and exo product, so that's two so far, plus the enantiomer of each. So plus enant, plus enant. Oh my god, can't write. All right, so just watch out for that. They could give it as they could ask you in a multiple choice, and they might, instead of how I chose to make this trans group dash, they could just make it wedged. All right, so let's go on to let's do a practice problem. Right, so we have this dienophile, okay, plus this compound right here, this dienophile with those NO2 withdrawing groups. All right, so let's just draw the arrows. Heat. And let's number before we go any further. 1, 2, 3, 4, 5, 6. One, two, three, 4, 5, 6. And actually, let me just put that on the inside so I don't waste room. 1, 2, 3, 4, 5, 6. All right, so we know that carbons 2 and 3 get the double bond, so just draw that line there. Carbons 2 and 3 had OCH3 groups, so let's put them like this. And before I even look at stereochemistry, I always like to draw everything planar, just so I have all the regiochemistry correct. Now, in this case, I didn't need to worry about, oh, where's the partial positive and negative, because this is symmetrical, and this is symmetrical. There is no difference in any way you can orient it. All right? And so, again, like I said, we don't need to worry about stereochemistry with these guys in general, because for carbons 2 and 3, because they are on carbons of double bonds, so there's no chirality there. And now we have to put the NO2 substituents on carbons 6 and 5. All right, so this is how you would draw everything planar. But now what about the stereochemistry? So over here, I gave you guys this little map, where it tells you what the trans and cis groups are. But here in this case, you can see that on carbon 1 and 4 of our diene, well, there's nothing there, right? Nothing that you can see there. But you guys know that these carbons with terminal double bonds, so like if I had this carbon chain, he has to have 2 hydrogens here. And so that's exactly what we have on carbons 1 and 4. So let me clear some space. Let's pick a different color. Here's 1 hydrogen. Here's another. All right, and let me make it the distinction better. Same for this guy. So how do these hydrogens correspond to this T and C thing, right? Now, because they're both hydrogens, it doesn't really matter, right? But just to keep it consistent, you can see that this hydrogen and this hydrogen are on the same side of the diene, right? Actually, let me redraw them. That's probably better. All right, so these guys are on the same side of the double bond. They're the trans groups, right? The trans groups point outwards in the diene. These inward-facing groups, right? You see they kind of point inward. These are the cis groups, and you can see that they have the same stereochemistry there relative to each other. Okay. What about on our diene over here? Sorry, dienophile. These carbons 6 and 5, the only thing they're missing that we did not write in, right, is going to be the hydrogens. Right? That's the only thing we're missing in here. So, relative to the NO2, these two NO2s, these guys have the same stereochemistry as each other, opposite from the NO2s. So now let's try to draw in the stereochem. So I'm just going to draw in those hydrogens. Okay, so here are hydrogens, both planar. And so we know that one of them has to be wedged, one of them has to be dashed, right? So I'm going to pick to make these trans hydrogens, I'm going to make them wedged. All right? Arbitrarily, doesn't matter. They're both the same hydrogen, so it doesn't matter which one you pick. So here's that wedged hydrogen. And then here's that other hydrogen that we said was this guy, this other trans hydrogen. We have these two hydrogens, right, that have the same stereochemistry as each other. but they have to also have opposite stereochemistry as these trans hydrogens. So if we made the trans hydrogens wedged, the cis hydrogens get a dash. Okay? Now what about our NO2s? We said that we want to have the trans substituent. This trans substituents have the same stereochemistry as the electron withdrawing group. I made my trans substituent wedged. Therefore, my electron withdrawing groups must be wedged. Right? And this guy over here, he also has to be wedged, right? Because he is on the same side as the NO2, as the other NO2. They have to have the same stereochemistry. So this guy gets a wedge. Now you may be wondering, was it important to actually draw these hydrogens out on a multiple choice? Maybe not, right? But let's just try to draw that exo product version, right? So here's our electron donating groups. These are our hydrogens, and like I said, I picked the trans hydrogen to be wedged. You could have made it dashed as long as you just kept the NO2 the same, consistent. Now in the exo product, right, here's the endo, where the trans groups have the same stereochemistry as the withdrawing groups. The exo product has to have the trans groups opposite stereochemistry of the electron withdrawing group. So in this case, our trans substituent was that wedge. That means, and we made the NO2 wedged. In this case, we make the NO2 dashed. All right, and now we have the exo product. Right? Now in this case, there isn't really much of a distinction between them because these substituents are exactly the same, right? So you could technically take this guy and flip him onto this guy, and you'll be able to superpose them on each other, right? So this would not be that good of an example, but it is just showed how we would approach this from a hopefully not too complicated example. And now we can go on to like one that you'd more likely see on an exam, right? That's going to be this guy over here. Choose the major product of the following Diels-Alder reaction, right? So you can see that we have this diene, and I'm going to redraw everything here. And here's our dienophile. All right, and we react it with heat. So first thing we have to do, we have to determine how our Diels-Alder connects, right? Where's that partial positive and negative? And for that, we use resonance. Remember, this oxygen has 2 lone pairs. I can bring one of these guys down, forcing this double bond over here, and this double bond goes onto that carbon in the form of a lone pair. Now we're going to get this resonance structure. You still got that one lone pair. The double bond is here, and we put a negative charge on that carbon. So what I'm going to do is I'm just going to put a blue dot on that carbon to know that that guy has a partial negative. Now with our withdrawing group, or our dienophile, we can bring this double bond up and that double bond too, giving us this resonance structure. O minus, double bond over here, and a positive charge on that carbon. So I'm putting a blue dot here, telling us that's where our partial positive is. All right, so let's erase these resonance structures. Now we know where everything is supposed to go. Okay, and so we want to connect that negative to that positive. All right, and so let's draw our 6-membered ring. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The double bond is going to form on 2 and 3. Off carbon 1, we have the OCH3. And on carbon 6, we had this ketone, right? That withdrawing group. So we want to connect our carbon 4 and our carbon 5. So that's exactly what we did. That negative is supposed to be connected to the carbon of that positive, right? So that's everything planar. Now they showed stereochemistry, so we usually want to always show stereochem. So and they're asking for the major product. The major product in the Diels Alder is the endo product, where the trans substituent of our diene has the same stereochemistry as our electron withdrawing group. So what is our trans substituent? So I'm going to clear some of this up. So what's our trans substituent? Remember, the trans substituent is this outward facing group, right? Now you don't have to always keep referencing this diagram. I just find a lot of people, I found a lot of people think that it's helpful, right? But we call it trans because if you cut this double bond down the middle, right, as if you were trying to determine E and Z, you can see that this guy, the major, the highest priority group on this side of the double bond is pointing upward. It's this OCH3. And the highest priority on this end of the double bond is pointing downward. They're opposite from each other. That's why we're trans. That's why we call it trans. All right? So that's the trans substituent. And off of the other carbon, it's just going to be a hydrogen. What are the cis substituents, the inward facing groups? Well, nothing's written, so it's just going to be a hydrogen for both of these carbons. And our electron withdrawing group is this guy right here. All right? Now you see, we don't need to really worry about the hydrogens in terms of stereochemistry, right? It's because if you knew this guy, you would be able to figure out the rest of it, right? If you just knew the principle. So we've established that this substituent is the trans substituent, and here's their electron withdrawing group. The endo product, the major product, will have those two groups the same stereochem. So whether you want to make that dash or wedge, it's up to you. So I'm going to make it dashed, which means that this guy must be dashed also in this pointer. All right. So that would be the product, and that's going to be answer choice B. Now, if you chose to make it wedged, right? If I, let's say, drew this as wedged, you can see that that's not an answer choice here, right? So what that all that means is you just picked the enantiomer that they did not draw, because remember, we have two enantiomers when we do the Diels Alder, and as well as the endo and exo product. So endo exo, right? In this case, this is the exo product, the minor product, because the trans group is opposite stereochemistry of the electron withdrawing. The endo product, the trans group, is cis, or same, it has the same stereochemistry as the withdrawing group. All right. They also have their own enantiomers, so you're going to get and I didn't draw the double bond there, right? Plus all right. So you see we have our endo, exo, plus the two enantiomers, and then the endo has two enantiomers, and the exo has two enantiomers. So you see that I drew this wedged enantiomer. They didn't have that. But all you just need to do is know, oh, okay, so the other enantiomer is just all the chiral centers flipped. So that means instead of all wedged, it's going to be all dashed. So that's going to be B. Okay? So that's how we did that problem. One more. Choose the diene and dienophile that would give the following Diels Alder product. All right? That's actually weird. The question is not All right, disregard the question because it's asking to choose a diene and diene file when they've given it to you. So all we're going to do is just find the major product. All right. So I do not like when I see a Diels Alder looking like this because it kind of can throw you off. So I always put a reorient everything. So we have this our diene, and we have an OMe group, which is just OCH3. And we have our diene file. Remember, when you're redrawing it, just make sure to keep it consistent. You see that our CO2Me and that methyl are opposite each other, right? So you would want to draw like this, that methyl. And in case you guys were a little bit concerned what CO2Me is, since that all it is going to be this. You should get used to that shorthand that they could use to write it, right? So that's going to be our diene, and that's our diene file. Now, whenever we do the Diels Alder, first thing first, regiochemistry. So where's that partial positive and negative? Start with the diene. It's got those two lone pairs. Move one over there, right? So we're going to form a double bond there, but now we have to, we're going to have to move that double bond on this carbon. Remember, do not move it over there. You're going to break an octet. Move it over there. That's going to give us our resonance structure. Positive charge on that that oxygen with still one lone pair left. And this carbon now has a negative charge. So I'm going to put a blue dot on that carbon. That's our partial negative. So let's clean that up. Now on our diene file, we can bring this double bond up and that double bond as well. O minus, double bond there. And now this carbon has a positive charge. So I'm going to put a blue dot on that carbon and write partial positive. So we now know where our partial positive is. All right, and so now let's number it. 1, 2, 3, 4, 5, 6. Draw our 6-membered ring. That was weird. 1, 2, 3, 4, 5, 6. Double bond on carbons 2 and 3. All right, and so we want to connect carbon 4 and 5. All right, so that means we're going to have a bond right here. So on carbon 3, I'm putting MEO. Carbon 6. Okay, so you want to be always careful. Make sure that partial negative and positive line up. Okay, if you do not do that, you're going to get the problem wrong. Because the stereochemistry can be tricky, but if you don't get the regiochemistry right, then it doesn't matter if you got the stereochemistry, because you're going to, the regiochemistry alone is going to mess you up. Okay. And so what I want to do now is I want to write CO2Me like they did, because I want to get you guys used to that. So I'm just going to erase this guy over here. All right, so here's CO2Me. And we still have that methyl to worry about on carbon 5. So let's just put the methyl there. Okay. So now we have everything planar. Let's focus on stereochem. We said that our trans substituent on our diene, right here, here's our diene, must have the same stereochem as the electron-withdrawing group. So here's our electron-withdrawing group. What are the trans substituents? So let me just erase the numbering here to make it easier. Well, we don't have anything written on those carbons, so that means that there's only hydrogens there. One hydrogen up there, another there, one pointing inward on that carbon, and another pointing inward on the other carbon. So the trans substituents are these outward facing groups, right? So that must be the same stereochemistry as our electron withdrawing groups. So let's just make the hydrogen dashed. So I'm making the trans hydrogens dashed. And remember, they get the same stereochem, right? They are the same side relative to each other. The cis hydrogens are these guys. Let's make them wedged because they have to be opposite the trans hydrogens. And again, like I said, this can be, I know, a little bit confusing, but the more practice you do, the better you will get at it, all right? And you'll be able to get through these problems much faster. So we said the trans hydrogen has the same stereochemistry as CO2Me group. We made the trans hydrogen dashed. So let's make the electron withdrawing group dashed. This methyl right here, we still have to fix that stereochem. The methyl, if you put a line through this double bond, it's on the opposite side of the electron withdrawing group. They're not the same side. And so what we're going to do is you have to now, since we made this withdrawing group dashed, this has to be opposite wedged. All right, that would be the endo product. Now, again, because there's just hydrogens, it doesn't really matter the stereochemistry here, right? But we just wanted to practice. And this MEO doesn't get any stereochem because it's on a carbon of the double bond. So what's our answer going to be? Our answer is going to be C. Now, again, you could have just drawn the other enantiomer. That does happen, which would have been this. Right now, and if that happens, just draw the other one because you'll realize it's not an answer choice here, and you'll get C. Okay, I hope that clears it up in terms of how we do stereochemistry when both the diene and dienophile have substituents. All right, take it step by step. You guys will be able to do it fine. All right, I will see you guys in the next video.